The first module that I want to talk about is our random number generator that is really just a counter that increments on the clock. Since there are 7 possible game pieces in Tetris, as soon as the count reaches 7, it resets back to 1. This allows us to get a number that is random to the user that we can assign to the shape of the piece. Using a case statement, that random number is then assigned to one of the 7 shapes of the Tetris pieces. It is also important to keep track of the number of 90-degree rotations the user wants the piece to rotate. We do this in a finite state machine where each state corresponds to one of the 4 orientations of the Tetris piece. We use this to assign an output to the orientation, which allows us to create the correct piece for the player. Using a code found on GitHub from a previous project, we were able to define the 4 individual blocks that make up the Tetris pieces and move them around to make the 7 different shapes with 4 different orientations each.
For this snippet of code, this is in our FSM, and this is a 16-bit counter, which is described as CNT, and it's used to generate a clock signal with a certain amount of cycles of the original clock, and the signal is utilized in a register which is named cell reg to control the selection of digits for display. The game's score is represented by player score, and it's divided by 10 to get the remainder, which is stored in the current digit. The code then shifts to cell reg again on every rising edge of the clock, which cycles through the digits. So for each digit, the 7-segment display and is used to determine the display pattern, and both those are generated. In this snippet of code, it is from the keyboard module, and basically it handles keyboard input and uses a synchronous serial communication protocol. Synchronizes with the negative edge of the clock signal, which is K clock F, and the counter, which is described as CNT, keeps track of the different phases, and it receives bits of data from the keyboard, and as each bit of the serial data is received, during the clock cycles, it updates corresponding to the data curve buffer. This snippet of code represents the clock divider module. So basically, the pause condition, it checks 2 counters, which is the VGA counter and the game counter, to determine when to toggle the clock signals for the VGA display, and also for the game clock. These counters are incremented until they reach half of the target frequencies, which are described as the VGA target frequency and the game target frequency. And that's when they're toggled and they're reset to 0. And this basically divides the system clock frequency to generate synchronized clock signals for the display and the game logic. It basically ensures that the clock division only occurs when the game is not paused. So it allows for both timing control and display windowing. This code snippet is basically the levels and the difficulty progression in the game. It checks for the full lines and it updates it based on that, and that is the row states. It awards the player 100 points for each cleared line, and it transitions back to different states based on the level that you're currently on.
Here's a bit of code that we referenced for the block falling. The code is from the following GitHub account for an FPGA Pong game. The x position of the block is set to x position plus dx, and the same is done for the y position. The y position is updated with the positive edge of the clock and goes down 1 each time that the clock comes around. The x position depends on the user. If the user presses the left button, the block will move left, and the same goes for the right button. Ideally, this would all be done with a counter to create somewhat of a delayed look instead of moving by a set value, which more so relates to speed in this case. This would have given a more traditional Tetris movement where the block moves by 1 grid unit each time.
Okay, now moving over to the VGA aspect of our project. So I didn't have the time to combine all of the modules into one, so I'll just be giving you a little demo of what should have happened if it were to work, and we had more time to combine all of the modules. So first, taking a look at my VGA controller, I'll be converting the positions of the block into two X and Y coordinate in which I want my squares to be shown on the big screen. And initially, I wanted the shapes to be sprites, but I didn't really understand the concept of reading from a ROM and writing to the ROM using Verilog. And due to the deadline coming up, I'd given up on the idea and had rather changed to just displaying each squares that makes up the shape itself. So this module will be taking in one X and Y coordinate of the center of each of the squares, and the output is going to be the bottom left and the top right coordinates of each block that I want to show. And the way that I'd gotten the X coordinate of the bottom left corner is with the equation below. So with this equation, and with the position of the block where the X is 6 and the Y is 3, the green one. So I'll be plugging in block 1 X will be 6, and the block width will be the pixels that that we needed to represent the width of each square. And in this case, it is 17 pixels, and the block radius, which is the distance between the center of each square to one of the side, and that will be 8. So then doing the math out, we get 94, and converting 94 from decimal to hexadecimal, it'll be 5E, and that matches with what our test bench shows. Alright, now moving over to our top VGA module. So in here, we can see that our horizontal sync and vertical sync are working. So that's great.